Okay, so last time I explained what limit comparison test is, but I think this is best understood if you see more and more examples. So let me try these questions again, but to give you a rough idea of what limit comparison theorem is doing, so having the limit an over bn to be L as n goes to infinity means that when n is very big, an over bn is somewhat close to L. Okay. So that an is something like some L times Bn. Now we're talking about the sum of these numbers, right? Ans and Bns. So suppose we know that Bns add up to some finite number, then An would be also adding up to a finite number times L, about. Right? So if two lists of numbers where one list is an infinite series where if you add them up, let's say it goes to 4. Right? And this L is, say, 3. Then if you add up the second list, which is about 3 times the other list, the sum will be about 3 times 4. Right? So if this one converges, this one should also converge as well. Right? Now that's not to say that you can estimate the sum of an by using L times Bn. It's a little different because initially they might be very different. What this limit is saying is that they're very similar, or one is L times the other when n is a really big number. So if you only take the tail of a series, then one will be L times the other. Okay, but just keep that as an idea. All right, so here's our problem. And by the way, because there's so many things going on, it's often easy to lose track of what's really the question. So let me start over by talking about what we are trying to do here. Here we have the sequence 2 to the n plus 5 over 3 to the n plus 5n. And that sequence behaves like 2 to the n over 3 to the n when n is really big. Do you see that? Okay, so what I want to say is that in that example above, 2 to the n plus 5 over 3 to the n plus 5n is pretty much like 2 to the n over 3 to the n when n is really large. Because, look, if n is like 10, this is already in thousands. 5 is very small compared to that, right? 3 to the 10 is even bigger. Now, 5n is a lot smaller than 3 to the n because of it. So if you just take the dominant terms of the top one and also the bottom one, you can see that this thing will be pretty similar to 2 to the n plus 2 to the n over 3 to the n. Okay? Now this is important because that immediately tells you that the limit will be what? Limit of n going to infinity of 2 to the n plus 5 over 3 to the n plus 5n is what?
2/3.
Well, 2/3 to the nth power. What's that?
Oh, infinite.
Okay, 2/3 is like 66.67%, right? So it's like if you multiply something by 2/3, it's like taking 33% discount. So let's say you went to buy some clothes and the store clerk didn't understand the coupons properly, and he just takes any number of coupons that you give to him. So you just have like 100 stack of 33% coupons, and he just applies it over and over again. What do you pay at the end of the day? If you get 33% discount over and over and over again, you get 0, right? Yeah. So 2/3, when you take n to infinity, you get 0, right? Yeah. You multiply 2/3 to itself, it becomes smaller, right? And it gets smaller and smaller and smaller. Gives you 0, right? Okay, so what we know is that if this is not 0, then there's no hope for the summation to be finite. But because this is 0, we have some hope that the summation may be finite. We don't know. It could be infinity still. But I guess this is the point that a lot of people don't understand. See, when we have an infinite series, in most cases, we don't know the actual value of it. The answer in closed form is, in most cases, impossible to compute. Okay? So what you have to do is, like, you just truncate this series at some point for the first 1,000 or 1,000,000 terms and say, hey, that's the approximate value of this. But the problem with that is, what if the summation goes to infinity? Then no approximation can be said to approximately true, right? It's very different. So whenever you have an infinite series, your question is always, does this converge or not? Because if it converges, then you can happily truncate at some point and say, hey, this is the approximate value. If it does not, then there's no point in approximating, right? So that's why we want to ask that question. And the first thing that you want to settle is figure out whether the limit of the sequence, this part, is 0. Because if it's not, then immediately there's no point in doing anything because it diverges, right? However, if it does go to 0, then now we have to figure out ways to find out whether it converges or not, because that doesn't tell you if it's going to converge or not. Okay? All right. So now let's actually try to apply the limit comparison theorem. The limit comparison theorem does this. You're trying to figure out the convergence of an infinite series, but that looks very complicated, like this example. It's really complicated, right? And what you want to do is you want to come up with something that's simpler, easier to figure out whether it converges or diverges, but it is somewhat comparable to the original series because one is some L times the other. Okay? So what do we want to compare this with?
2n over 3n.
Yes, 2 to the n plus 5 over 3 to the n plus 5n is very much like 2 to the n over 3 to the n, right? So because of that, we can just take limit n going to infinity of this thing, and well, we already know the value of the limit, right? Because this is very similar to this one, so in the limit it will be equal to 1. Right? So that's one way to do it. Or if you insist in actually writing down the limit rigorously, you would do limit n going to infinity. It's a keep, change, flip, right? So keep the top. And then you flip the denominator up, multiply, so you have 3 to the n here, 2 to the n here. And when you multiply, this is limit n going to infinity. 3 to the n times 2 to the n is 6 to the n, times 5 times 3 to the n. 3 to the n times 2 to the nth is 6 to the n. 5n times 2 to the nth is 5n, 2 to the n. And at this point, you can already make an argument that 6 to the n increases much faster than the other one, so these are the dominant terms. And since they are the same, the limit is 1. Or if you're still not sold on that idea, you can divide top and bottom by 6 to the nth power. Anything divided by itself is 1. 3 to the n divided by 6 to the n is 3 over 6 to the nth power, which is 1/2 to the nth power. 1 plus, in the same way, 2 over 6 is 1/3, so 5n times 1/3 to the nth power. Limit n going to infinity. And this becomes 0, this becomes 0, so it's 1 over 1, right? Which is not equal to 0. So we've managed to satisfy the condition, okay? Now, what does that say? What does that say? That the convergence or divergence of the original series follows the convergence and divergence of series for 2 to the n over 3 to the n. Okay, so tell me what the series of 2 to the n over 3 to the n means. What do I mean by that? Series of 2 to the n over 3 to the n. I mean by the sigma. Okay, sigma is the series, right?
Yeah.
If you have the sigma, it's a series. Without the series, without the sigma, you say sequence. Okay. Without the sigma, you say sequence. Okay. So we're trying to. So this was the sequence, 2 to the n over 3 to the n. Now we put it inside the sigma notation. And we now have to figure out whether that converges or not, because the convergence and divergence will follow the convergence and divergence of this. Okay, so tell me whether this converges or not. Can you see whether this converges or not?
Converges.
Why? Why does it?
Geometry.
Yes, that's very good. Okay, so if you are still not sure, you can write them out. If n is 1, that's 2/3. When n is 2, is 2 squared over 3 squared, which is 2/3 squared. 2/3 cubed. This is a geometric series, right? Geometric series with r equals to, common ratio is 2/3. And if the absolute value of the common ratio is less than 1, we know that it converges, right? And therefore, summation n from 1 through infinity of 2 to the n plus 5 over 3 to the n plus 5n converges by the limit comparison test. So that's what I mean by using the limit comparison test. Okay, so I want you to try this second question. Again, what you want to do is you want to obtain the sequence that you want to compare it with by ignoring the less dominant ones and only thinking about the dominant terms. If you take the dominant one, then you get a simpler series, and from that you may be able to deduce the convergence and divergence. Okay, so let's do this together. So because we don't know any concrete series that converges or diverges, we really don't have many things to compare it with. It's only one of these two. One is what we just did here, which is summation of AR to the nth power, which converges to A over 1 minus R, but this is only valid if the absolute value is less than 1, right? So that's called the geometric series. And the other one is what we call the p-test, right? 1 over n to the pth power. This we know to be divergent if p is 1, right? If p is 2, it's convergent. Right? And anything in between, here's the criteria. If P is 1 or less, it diverges to infinity, right? And if P is greater than 1, then it converges. Okay, so that's called the p-test. And then we have some telescoping series which also converges, but that's usually not easy to compare with. So you really have just two choices, you might think. Okay? Yeah. In most cases, when you're applying the limit comparison test, you just have this or that. Okay? And that's a good thing to know because look here. To get the sequence to compare with, you just write down the dominant one, which is n cubed dominates every other one, so it's really like this one. But what is that? That's like 2 over n to the 3 over 2. Right? So that's like the p-test, right? The only difference is p-test, you have 1 on the top, so let's just choose 1 instead of 2. Okay? So we can compare this one with this one because I know that this converges. Okay? So let's.
Because you could just bring the 2 out as a.
Oh, because if you take the ratio, you're going to get 2. 2 is, as long as you get a number that's not 0, then we're good. Okay, so here, limit of n going to infinity of 2 over square root of n cubed plus 2n plus 5 over 1 over n to the 3 over 2 power. Okay. The same thing as limit of, well, it's like this. If you have a over b and then you divide by c, that's like multiplying c in the denominator, right? Do you agree? Dividing by c is same as multiplying by c in the denominator. So I'm going to use that rather than usual keep, change, flip because this time it's easier. So this will be limit of 2 over, this gets, so 1 over square root of n cubed. This is the same as 1 over square root of n cubed. I'm just going to multiply this in the denominator. Okay. And the reason I like that is because then when this gets multiplied inside, these are all divided by n cubed, which is limit n going to infinity of 2 over square root. N cubed divided by n cubed is 1. 2n divided by n cubed is 2 over n squared. And then 5 divided by n cubed is 5 over n cubed. And now you can easily see that this is 0 as n goes to infinity. Right? 2 over infinity is 0. And you just get 2 over 1, which is 2, and that's not equal to 0, just as our limit comparison test requires. Since it meets the condition for the limit comparison test, now we know that the convergence or divergence of this series follows the convergence and divergence of this series. Okay. So you turn this sequence that you compared with as a series, as an infinite series. Infinite series means you put the sigma here, okay? And then because this is a p series, with p equals to 3 over 2, which is greater than 1, what's that condition? That case is convergence. So we know that this converges. So summation from n equals to 1 through infinity of 2 over square root of n cubed plus 2n plus 5 converges by limit comparison test. It's very important that you write the name of the test because or else I can't not understand your logic. Okay? By writing the name of the test, I know what logic you're using and therefore I can understand your proof.